Now we'll look at alternating series. So these are the ones that switch between positive and negative. So for instance, let's consider this series where the signs strictly alternate. Negative 1 to the k plus 1 over k, which gives us 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc. And this factor, negative 1 to the k plus 1, or negative 1 to the k, is what's going to provide our alternating signs. The exponent of k plus 1, or k, is just determining whether it's our first term that's negative or the second term. So let's figure out what's different about our alternating series by working with this alternating harmonic series. So whenever we look at a series, the idea is we're looking at the sequence of partial sums. So in this case, the first one is 1. Then we have 1 minus 1/2, which is just a 1/2. 1 minus 1/2 plus 1/3 is 5 over 6. 1 minus 1/2 plus 1/3 minus 1/4 is 7 over 12. And we can see that this is definitely doing something different than our regular harmonic series. So the alternating series test actually says if we have an alternating series, it'll converge provided the terms of the series are non-increasing in magnitude. So if I ignore the signs, I always have a k plus 1 is less than or equal to a sub k. And the limit as k goes to infinity of a sub k is equal to 0. So now, for instance, let's look at this term, the alternating series of 1 over k squared. So the first step is to look at, to see a sub k plus 1, which is 1 over k plus 1 squared, and ak, which is 1 over k squared. We can see that k plus 1 is greater than k, which means k plus 1 squared is going to be greater than k squared. When we flip our fractions, 1 over k plus 1 squared will be less than 1 over k squared. So this satisfies our first condition. The second condition said the limit as k goes to infinity of 1 over k squared was 0, which it is. So we've satisfied our second condition. So this series will converge. Now let's look at this series. 2 minus 3 over 2 plus 4 over 3 minus 5 over 4, etc. So if I look at my individual terms, I have 2. This is 1 1/2, 1 1/3, 1 1/4. You can see that my terms are getting smaller. So I do have that ak plus 1 is less than ak. So that term is satisfied. The limit as k goes to infinity. Well, first we need some kind of form. We can see the first term has a 1 on the denominator, the second term has a 2, a 3, a 4. So the bottom term is just a k. On the top, I have a 2, a 3, a 4. So you'll notice that's just k plus 1. The limit as k goes to infinity here is 1, which means this series will diverge. Now let's look at this particular one. So we know that the natural log of k is less than k. In addition, we have the limit as k goes to infinity of ln of k over k. Like I said, the natural log is less than k, which means k is growing faster. The denominator is getting bigger quicker, means my limit's 0. So the second condition is satisfied. As far as the first condition, a sub k less than a sub k plus 1, the easiest way to do this will be to think of the function f of x, which is ln x over x. And if we look at this function on a graph, it starts negative, it comes to be positive, and then it starts to slow down and slope off. So we can see that yes, these terms are non-increasing. As we move to the right, we are decreasing. So my second condition is also satisfied. So this series will converge.